Hello, my people. Hope we're doing well today. Just like in class, we're going to go over trapezoidal rule in this video, and we're going to relate it to what we already know about Riemann sums, left hand, right hand, and we'll mention the midpoint because occasionally it does show up on the AP exam. Although in terms of our conceptual understanding, it's a little more trouble than it's worth, but we'll cover it. Let's go ahead and consider the following function, negative 1/12 x squared x minus 6. Okay. I notice that, and I chose this function specifically because I wanted to deal with it over interval of 1 to 5, and so I wanted zeros here and here, and this, of course, 0 of tangency because of the x squared. This a 0 that actually goes through because it is of the first degree, and of course a negative out in front to give us the end behavior we need so that we have sort of a positive hump right here in the first quadrant. Okay. Now let's go ahead and say that we are being asked to approximate the area under the curve from 1 to 5 using a right hand Riemann sum. Now, right hand Riemann sum basically means that for each interval, okay, and let's do, I forgot to put this part, let's do 4 subintervals. Okay. So n is equal to 4. So that basically means that my first subinterval is here from 1 to 2, second subinterval here 2 to 3, third subinterval 3 to 4, and fourth subinterval from 4 to 5. Now, on all of those, if I'm doing a right-hand Riemann sum, I need to define the height of the rectangle that I'm going to use based upon the function value at the right hand of each of those subintervals. So go ahead and mark those heights, and we get something that looks like this, okay? And from the way that this one shakes out, we can see the fact that this is going to be a little bit of an overestimate, right? The only rectangle that is underestimating is this one right here, and that right there, probably is about the same as this one. So you have 3 pieces that are above the curve and 1 piece that is below. So this is going to be an overestimate. And here, let me finish coloring this in so it's all nice and pretty. Okay, now what we need, and I guess I should have put this a little further down the page, basically what we're doing here is our right hand Riemann sum, okay, is equal to, well, we need the delta x. Well, delta x, of course, is this b minus a over n that you see here and you see here. It's the entire interval, which in this case is 4, because it's 1 to 5, divided by the number of subintervals, which is 4. So 4 divided by 4 is 5. So every single one of these rectangles has a width and a height, right? Now, the width of this is going to be 1. The height of this is going to be f of 2, okay? So this is f of 2. Again, this one is going to be a width of 1, and this one right here is going to be f of 3, the output at 3. This one right here is going to be a width of 1, and a height of f of 4, and this one right here is going to be a width of 1 and a height of f of 5. So that should basically tell us that it's 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. Now, if I actually want to get those values, it shouldn't really be all that difficult. Let's go ahead and go into our y equals. Now remember, the function itself was negative let's go ahead and get a fraction for the 1/12, x squared times x minus 6, right? And we can go and look at the graph if we want. Window 6, no, zoom 6. And we'll see a little bit more of it here than we did in the one that I basically pulled off of a graphing program and pasted into this document. But there it is. So if we want to go to the home screen, and we realize that of course the ones don't matter, so if we want to use our calculator to evaluate this, we're going to do y of 2 plus y1 of 3. And I do love the fact that you can use these like function notation. You're probably too young to know this, but it wasn't always the case. And our sum is 25 thirds. Well, that's kind of nice. Okay. Now, if we wanted to do it by, more subdivisions, let's say, for example, we wanted to do it by, let's say we wanted 8 subdivisions. At that point, our delta x would, of course, be 1/2. And our right-hand sum, remember, right-hand sums don't start at a. They start at a plus delta x. So it would be, 1/2. And since it's a common width of all of the subintervals, I'm going to go ahead and factor out that delta x out here. And this would be f of 3/2 plus f of 2 plus f of 5/2 plus f of 3 plus f of 7/2 plus f of 4 plus f of 9/2, which is 4.5, and then f of 5. Now, thankfully, if I want to do it in my calculator, I don't have to do all of those, since I've already done the ones with the integer, the ones with the whole number inputs. All I have to do is add to that y equals 1.5 plus y equals 2.5 plus y1 3.5 plus y1 4.5. We just have to remember that when we get this sum, we need to chop it in half. So, and then divide by 2, and we get this lovely right-hand approximation of 8.042, right? Well, I mean, this was 8.3 repeating, so, and this was, we knew it was going to be an over, right, an overestimation. Now remember that when you come up here and go from 4 to 8 subdivisions, you're going to get a better approximation because you are functionally chopping away that piece right there, right? And and you're chopping away that bit of the overestimation, and you're chopping away, and that one's not that impressive, but you're still chopping away a piece of the overestimation. Now over here, obviously, you're basically chopping away some of the underestimation, so that's going to run in the opposite direction. But notice, of all of the things, obviously the pink are the 4 subdivisions. The outline and the Sharpie are 8. You subtract that, and add that back, and basically you have, you add this part back, and you have something that has gone down in value, right, and is obviously a better estimation and is closer to the actual value. Okay. Well, let's go ahead and let's talk about it. Well, let's save the formulas for the end when we start talking about it. Now, if we're looking at a left hand, now, like I said, I always do the right hand first because it's always that a plus delta x. For a left hand, you actually start at a, so you kind of have to back it up one iteration of delta x for the inputs, which is, of course, where this k minus 1 comes from. But we'll discuss that a little bit more here in just a moment. Now, again, we're going to start off with subintervals 1 to 4, and let's go ahead and do 4 subintervals again. And we're going to define it by the left hand. Okay, and we're going to get now remember that a lot of these, like 3 out of the 4, are the same size rectangles as we had before. They're just in the adjacent subinterval, right? They're just not where they used to be. Because in the right hand, this point was defining the rectangle over here instead of over here. This point was defining the rectangle over here rather than right here, and you know, et cetera, et cetera, et cetera. Now, this is obviously an underestimation, right? We have 3 rectangles that go under the curve and leave a little bit of a gap, and only 1 that goes over the curve right here. This is going to be an underestimation. Now let's go ahead and let's save the formula for a little bit later. Let's go ahead and let's do the left-hand Riemann sum. The left-hand Riemann sum for this is going to be, well, again, I have the width of all of these is going to be 1. Right. And I did, you know, the only reason I did it that way is not to make it easy, but to basically, in terms of us reviewing the Riemann sums, I didn't want us to be distracted by burdensome arithmetic. I just wanted to review the sort of concept of Riemann sums before we fold it in, with the trapezoidal rule. Now, the left-hand Riemann sum is obviously going to be 1 times f of 1. Plus 1, that's again the width of f of 2, 1 f of 3, and 1 f of 4. Okay, well, let's see what that gives us. We can go y1 of 1 plus y1 of 2 plus y1 of 3 plus y1 of 4, and that is going to give us 20/3. Okay, well, that's nice. And let's say again that I wanted to do 8 subintervals. Okay, so 8 subintervals, still doing left hand, but remember the delta x, of course, becomes 1/2, meaning the width of each of these. And what you have here is an underestimate that gets less under, right? Because you have left hand and then left hand. And so you're adding that little white square right there. You're adding it back in. So it's probably a rectangle, but you get the idea. Okay, so you're adding that back in. So the estimate is going to be less under than it was previously. Okay. Well, again, let's go ahead and do the left hand. Now we know that with 8 subintervals, the common width is going to be 1/2. So just like the last time, I'm going to go ahead and factor that out. And then from here, we start with f of 1, and then we add f of 3/2, and f of 2, and f of 2.5, or 5/2, f of 3, f of 3.5, which is 7/2, f of 4, and then f of 4/2, which is 9/2. Again, on our calculator, we've already done the ones for the whole number inputs, so let's just go ahead and add y1. And now remember, we're going to have to be careful once we get to the end of this, because we're going to have to divide it by 2. But we'll do that in 2 steps. 2.5, 3.5, and 4.5, and then we'll divide it by 2. And what we get here is we get 7.208. Okay, well that right there, remember 21/3 is 7, and so that's 6 2/3, and this is 7.2. Okay, we're going to come back to both of those numbers. But let's go ahead and look at a fresh graph. Now, the rectangles from the left hand and the right hand Riemann sum are different heights for each subinterval. Okay, I'm going to go ahead and do them again. I'm going to do the left hand in pink. Okay, I mean in orange. So we'll go ahead and need to sharpen that. All right, let me grab another one. Okay, and of course the pink ones are going to be here. And it's a little easier to, these sort of extend out. Okay. So what we have here is we have on each of these subintervals 2 things of different height, okay? So we have the orange and then of course the pink on top of that. We have the orange and then the pink on top of that. We have the orange and the pink on top of that. And of course on this last interval, as we've seen, it was the anomalous one compared to the rest. We have the pink, of course, with the orange on top. Now, when we're doing these trapezoidal rule problems, what we need to acknowledge is the fact that when we actually draw the rectangle, now notice that each of these subintervals has has 2 different rectangles, and of course the difference between them is also a rectangle. And so what we're going to do is we're going to draw the trapezoids that we know how to do, and we'll go ahead and we're going to use the Sharpie. Hopefully it won't be too thick, and we'll cut that in half, and then this one will also cut in half. And this one, see, I mean, we're drawing the trapezoid, but in effect, when we're drawing the trapezoid, we are actually cutting these difference rectangles in half. And if we're taking 2 quantities and chopping their difference in half, we are functionally getting the average of those, right? And so basically what needs to happen here is, and we'll go ahead and fill in the rest just with yellow. Now, that is a trapezoid. All 4 of those are trapezoids, and because basically what you need to do is you just need to, turn them like that to show them that they're trapezoids, right? We need, this base and this base. The average of them is going to give you the B1 and B2 for the formula of the area of a trapezoid there. And then here you're going to wind up with, again, taking both of the bases and averaging them and multiplying them by the height. But since we're sort of tilting them on their side in order to recognize them as trapezoids, we need to remember that the height is the delta x, right? And so what we get here is, so for this first subinterval, right, the base 1 is the height at 1, so it's f of 1, and the base 2 is f of 2, divided by 2 times delta x, okay? Well, let's go ahead and look at the second one. The base 1 is f of 2, and base 2 is f of 3. Then you take the average of those bases and multiply it by the height. Then you have f of 3 and f of 4, and you divide it by 2, and you multiply it by the height. And then you have f of 4 plus f of 5, and you multiply it, divide it by 2 and multiply it by the height. Now, basically what happens here is I need to basically factor out that 1/2. And the moment I factor out that 1/2, and of course if I had a meaningful delta x, I would also pull it out, because the delta x here, let's just go ahead and put the delta x as 1 just for the sake of being clear. But at that point, all of these double up, right? All of these double up except for the ones on the endpoint. Okay? And that's why you wind up having f of 1 plus 2 f of 2 plus 2 f of 3 plus 2 f of 4 plus f of 5. Now, let's go ahead and, now that would of course come from the trapezoidal shape of each of those subintervals. But as we discussed in class, one of the neat things as well that we realize is the fact that when we actually take the left hand, and I'm going to come back and do that evaluation here in just a moment. When I take the right hand Riemann sum, okay, and remember the right hand Riemann sum back here, the right hand Riemann sum looked like this. So it was f of 2, f of 3, f of 4, and f of 5. Okay, so f of 2 and f of 3 and f of 4 and f of 5. And when I take the left-hand Riemann sum, remember that that was f of 1 plus f of 2 plus f of 3 plus f of 4. Let's, just for giggles, add those together. So we get the right-hand Riemann sum plus the left-hand Riemann sum, and it's going to be f of 1 plus 2 f of 2 plus 2 f of 3 plus 2 f of 4 plus f of 5. Well, that looks a whole lot like what we got when we simplified using the trapezoidal rule, because it's exactly what it is. And of course, since this is the right hand and the left hand together, this is twice the approximation that I need. So if I then take the left hand and the right hand and multiply it by 1/2, I get exactly the same formula as I did for the right hand, from the trapezoidal, from using the area formula of the trapezoids. So what that means is basically that the trapezoidal rule is the average of the left hand and the right hand Riemann sum. And remember that the left-hand Riemann sum was 25 thirds. The right-hand Riemann sum was 20 thirds. That winds up being 15. You divide it by 2 and you get 7.5. Okay? And 7.5, of course, is 15 halves. That is the trapezoidal area, the area of the trapezoids added up. It is also the average between the left hand and the right hand Riemann sum. And so, I mean, like I said, you can think about it either way. It's just kind of nice, especially if you're given a problem where you're actually asked to use the Riemann sums and the trapezoidal rule to know their relationship to each other is more than just, you know, they're both, you know, this vague notion that they're both methods of approximating the area under the curve. Okay. Now, let's go ahead and do some examples. I think that will be instructive. Alrighty. Actually, let's go ahead and save the. Now that I've gotten sort of the conceptual stuff out of the way, let's go ahead and call it quits on video 1, and we'll do some actual problems here in the succeeding videos. If you have any questions, shoot me an email. Bye.